Okay, so there it is. It's uploading. I finally figured out if I go to Google Chrome, it goes much faster than on Firefox. But anyway, um, because YouTube is a Google product. I mean, they go hand in hand. My short discovery, my little discovery. You all could care less. Now wait a minute. Wait a minute. I just where the heck? There it is. I don't know how I turned that. I guess I accidentally turned that off. I didn't mean to. All right, so here we go. Newton's forces, laws of motion. Let's go from. I don't. There we go. Gosh, I'm having a heck of a time here. All right, two kinds of forces. Contact forces rise from physical contact. All right, like in the Chiefs game, if you saw yesterday. I got lucky. I just decided to watch the last quarter. Did you notice this has nothing to do with the lesson? But did you notice if you did watch the fourth quarter, there was actually no commercials because they were trying to get the game played and they knew it was exciting and they wanted to hold the audience. And there was like absolute. I mean, even after a touchdown, there wasn't a commercial break because they wanted to run the game so that they could get to the next one since we played at noon. So it was fantastic. It was almost like being there. And there wasn't all that standing around and an erectile dysfunction commercial every 45 seconds. But anyway, it's like typical, NFL. Okay, they advertise light beer, pizza, Rogaine for baldness, and ED drugs. Must be fat, bald old man who can't get it up. Anyway, so sorry. A force is a push or a pull. Contact force, action and distance forces. The moon causing waves, causing the tides, sloshing the tides around due to the gravitational pull of the moon, whipping around the Earth and the angular momentum that's causing, which we'll get into later. That's a force at a distance. Gravity is a force at a distance. Magnetic forces. Have you ever noticed you get a magnet? It can be pretty far away, and all of a sudden, things start to get attracted to it. All right, there's the classic scene in Breaking Bad where they put that van, smashed it up against the side of the police storage locker thing. But anyway, so gravity and electrical forces those are the forces that we'll deal with. Electrical forces next semester, but right now we're going to deal with gravity and contact forces mainly. We're going to attach things to things and pull on them, or we're going to hang things and see how gravity works. All right. Forces are vectors. All right, so if I was going to add these two forces, I'd take tail to put it there, go that way. The length of the arrow gives us the magnitude, and then the direction of the arrow gives us the direction of it. Mass is a measure of the amount of stuff contained in an object, and I gave you that whole thing on the kilogram. So Newton's first law. Now, get yourself off Earth. You must leave the planet Earth when we first start talking about Newton's laws of motion. Otherwise, if you don't get off Earth, you're going to be Aristotle. All right, so you've got to leave Earth. Aristotle, he thought that everything had an impetus when everything wanted to stay at rest at all times. That was the natural state of things, that they wanted to stay at rest because that's what he observed. He'd roll a ball across a marble floor, and it would eventually come to a stop. So he'd be like, okay, I gave it some impetus, and eventually it would come to a stop. He observed pebbles and different things. The problem was he observed things of different densities falling in water, through water, and he's like, oh, the heavier objects fall faster. We're going to find that that's not true. Well, we already know that that's not true, and from when we were looking at free fall. Okay, but so if we're out in deep dark space and we hit a retro rocket that accelerates us, let's say up to 15 meters per second, and we turn off that acceleration, we're just going to float in space. at 15 meters per second forever until we bump into something which provides a force that knocks us in a different direction, okay, or that stops us, or we fire the retro rockets in the opposite direction to bring us to a stop. All right, that's the way it works. Now, to change it, to compel it, to change that state by a net force, the net force is the sum of all the objects, of all the forces acting on the object. Okay? Okay, so here, I know it seems real simple at the beginning. This is very straightforward. I got an object here. 10 newtons pushing it this, pulling it this way, 4 newtons going that way, 6 newtons going this way. Same thing here. The net force on this one, they gave us a good old 3, 4, 5 triangle here. Going this way. So this thing, if it was out in deep dark space, it would be compelled to move this way. It's got a net force, and that net force is getting it to change its position, getting it to move. And it's going to accelerate. And the acceleration, the key part is the acceleration is in the same direction as the force. All right? Inertia is the natural tendency of an object to remain at rest, okay, the inertia of something, and we measure inertia with mass, all right? Remember that. Inertia is measured by, the way we measure something's inertia is by the mass of it. An inertial reference frame is one which Newton's law of inertia is valid, and all accelerating reference frames are non-inertial. What's an accelerating reference frame? You're in an elevator going up. It's accelerating. That's a non-inertial reference frame. An inertial reference frame is deep dark space. Nothing is moving. All right. There's no gravity. There's no nothing. So here on Earth, it is impossible to find an inertial reference frame. But since the Earth is pretty stable, because someone from Mars is watching us spin and all that kind of stuff. So we're moving and we're accelerating towards the center of the Earth. The Earth is also going around the sun and is getting accelerated towards the center of the sun. All that stuff. But for the most part, we're going to use the laws. We're going to use the Earth or our classroom or the lab as an inertial reference frame because all the acceleration is the same at 9.8 meters per second downward. So we're going to treat everything like that's the inertial reference frame. All right, mathematically, the net forces is written this way, the sigma. Okay, that's a piece of cake. And so now here it is, dun, 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 Newton's second law. When a net external force acts on an object of mass m, the acceleration that results is directly proportional to the net force, and it has a magnitude that is inversely proportional to the mass. When you read these things, it sounds hard. Basically, F equals ma. The sum of the net forces, it's the sum of the net forces, is equal to ma. All right, we're going to stop right there with this one.